Hey, John here. This video is a little overdue. Some years ago, I put together the Z80 Retro project. We moved it off into this GitHub repo over here. There'll be a link to this below the video on YouTube if you want to check this out yourself. If you're following through, I'm going to put this video earlier on in the playlist for the Z80 Retro series, because if you're just getting started with retro computing and you've never really gotten heavily into assembly language, you could get a little bit confused by the way the documentation is set up on here. So I hope today I'll bridge that gap. As always, a big thanks to anybody that assists and helps out this channel in any way, especially the VIP patrons listed here. There's links in the description of this video below if you would like to join the Patreon and become part of the party. Okay, so here we go. This is the Z80 Retro project repo. Inside here, you'll see the schematics where you can buy the PC boards and links to the video series on YouTube somewhere in here. Here you go, the Z80 Retro playlist right here. And among other things, you can find various manuals. Here's a manual that the internet community did a lot of work on putting this together on how to do this project and stuff. A lot of this is summaries of what is in the Z80 Retro playlist, part of which you're watching right now. So if you don't want to watch all the videos, you can maybe leap in and make sense of what's going on from here. I added this a while ago because when they open sourced and officially, finally gave away the source code of CP/M, which is only recently, I wanted to put a copy of all the manuals for CP/M in this website and make them easily available, because sometimes they're kind of hard to find, or you get a cruddy scan or a good one. So I've kind of gone around and collected some of the most reasonable ones I could find and put them all in here, and this README has links to them all, among other ones. Here's all the CP/M manuals, and click here, you'll get a PDF that pops up, or you can get the GitHub PDF reader version here, which I never don't much care for that. I like the PDF to open in my own browser, but that's why they're in parentheses and direct over here, the two different styles of reading them. And then, of course, one big book that has all the manuals in it. This one's more dubious. I wouldn't be surprised if I get some sort of a copyright thing about this and this goes away sometime, so you might grab your copy while it lasts, or at least go somewhere else. Are these actually local or not? Yeah, it looks like I have a local version in this repo. Okay, so there's also some other links that I mentioned over the course of time in my videos. All right, so what's the big deal? Up here is the big deal. I've been doing all the work with the Z80, as would anyone, for the reasons I will mention in a few minutes. On this project, and all my CP/M code and everything I wrote with Z80 assemblers, okay? And the reason we need to talk about this today is we need to talk about the 8080, because if you look at any of the documentation for CP/M, which was developed before the Z80 was ever invented, all the code, all the examples, and their assembler and their debugger are all designed to be used with 8080. Now, let's take a quick tiptoe through Wikipedia and look at the page for the Z80. It's an 8-bit processor designed by Zilog, blah, 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 by this guy, Federico Fagin, I believe. I've heard his name pronounced that way in front of his face in videos that I've seen on the internet, so that might be the right way to pronounce it. I don't know. Anyway, so it was released in 1976. The 8080 came out in like 1973. Discontinued only a few months ago. Very depressing. But the good news is that's a long time, and there is a huge number of these things floating around. Go find them on eBay. If you want to build this project today, you can still get them. But like I said, you might have to go to eBay. What else do we got in here? Common manufacturers are made by many different manufacturers. And this is why, in my opinion, it was so popular. It's because if you need to build a product and you want to be able to, make it for a while, you need to know that you can always get a processor. All the way up until 6 months ago, these were officially manufactured by at least a couple of manufacturers. and they finally went away this year. I wouldn't be surprised if somebody doesn't like pick it up, some low volume producer or something, if somebody really wants one, or a few million, you know. But like I said, you can get them on eBay, and you continue to be able to do that, I'm sure, for several years. Now, here's what's interesting. What do we got? Federico here, if you look at his history, where did he come from? Blah, 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 blah. Best known for designing the first commercial microprocessor, the Intel 4004. He used to work at Intel. After that, what did he do? He did the 8008 and then moved on to the 8080, which is the first in the line of all the processors that went to the 8085 and the 8086, the 186, 286, 386, 486, blah, blah, blah. All the stuff that's in the PCs even today, all the way goes back to the 8080. And if you've ever seen any assembly language source code for the PC, I'm air quoting while I'm not on camera, you'll see a certain similarity. So it goes all the way back to here. Okay, let's close this window and get back to our friends, the manuals. Now, the reason, like I said, we want to do this is because the CPM was written in 8080, the system alteration guide. I spent a lot of time talking about this in my Z80 Retro series. Here is this manual here, and I'm opening it now because this, along with many, many other manuals that you find about how to write a CPM program, very often, because they were written in the 70s, they will have 8080 assembly language in there. LXI, MVI, call, DAD, and increment, and stuff like that. See these instructions here? These are not Z80 instructions. JC is jump if the carry flag is set to that label, and so on. This is why you need to have at least a passing familiarity, in my opinion, with the 8080 assembly language source code that you see here, because if you're going to dabble with CPM, you're going to see a lot of code written in here, and if you're going to play around with just about any board anywhere that you want to build as a kit today, it will not have an 8080 on it, it'll have a Z80 on it. And while, as we'll see in a minute, you can still run all these same exact binary images from the 8080 on a Z80, which was by design. Same guy designed and built them both. So he made sure that they were backward compatible, and I'm air quoting, good enough to run programs that were designed for the 8080. I mean, obviously, that's what you want when you build a new processor. You throw it out in the market. You want to sell everybody, redesign all your code from scratch, learn all new stuff, and, oh, by the way, you need to come out with all new code. Well, it works for Apple, I guess, but in the modern days, but not back in these days. There's no way they would have gotten and survived this. But here's what happens. I'm sure they would have just used this assembly language and just said, here you go, here's another assembler, because it's binary compatible. Again, binary compatible enough to just take the raw binary, the whole operating system for CPM, written and assembled to run on the 8080 and put it on a Z80, and it just goes. No difference at all. And that's like I said, that's a great marketing thing to do, but you'd probably get sued by Intel. Most definitely, certainly back in those days, and even today. The machine language is kind of math-ish, which is not patentable or copyrightable per se. But the assembly language source, the grammar, is something that can be copyrighted and then licensed. And then you can go talk to Intel and AMD about that over all these years. I'm laughing because Intel actually has to pay AMD all the time to use the 64-bit instruction set as I understand it, because AMD is the one that designed it before Intel got around to using it. So actually, Intel licenses that from AMD these days. I don't Google it. Let me know in the comments if I'm wrong or how that really works. I read an article somewhere of that effect. That's why on a Linux machine, it's called AMD 64, not like Intel 64 or something like that in terms of the the machine architecture. Okay, so these source code names for the instructions were the things that that Zilog did not want to have to pay the license, okay? So what do? They said, look, let's just come up with a new language that's really similar, close enough, so that people that know one can adapt to the other, and that's why we're here today. But they all assemble into the same binary, at least for those compatible instructions, all right? So that's why I want to talk about this for a little while. If you're just getting into the game and I want to do this, I want to start from scratch, I want to experience what happened in the 70s, because you had all the folklore and all the other stuff. The beauty of this is that, yes, you can actually do this. I did it when I was 18 from scratch. Very little help from anyone at all. Much frustration, I would say, on various things that were hard to understand. A lot of cursing went into those days. But you can do it, okay? And you can learn assembler and get it all going. But it's a real kick in the butt if someone tells you, here's all the code, and then changes the language on you midstream. So let's try to spackle up that blemish here, okay? So let's get this out of the way and look a little bit at the 8080 Assembly Language Manual. There's two manuals that I have links to here. Wait a minute. There's one other thing we probably should look at. Again, I'm back here on the Wikipedia page for the Z80. Down here, this is what we want to look at. They have a copy of this ad. Well, they got a date on this somewhere. This is in 1976, I'm sure. In late 1976, when the Z80 was first made available, they wanted to explain what is the difference between the Z80 and the 8080. This is why you're not going to use the 8080, okay? In order to use an 8080, you have to have +5, -5, and +12 volts just to power the thing. The clock has two separate phases of non-overlapping. No, you actually have, they make a special chip just to generate this wonky clock that they need to use, and it has to run at 12 volts. The Z80 over here only needs 5 volts. It needs a single phase square wave clock running at 5 volts, which anyone can get from a metal can oscillator or generated very easily with a crystal and a CMOS inverter or something like that. Runs a little bit faster, so that would have excited everybody. And it's 20% off the speed here, right? In terms of the clock period. And this is the other thing. If you use an 8080, you need to have it, a couple of chips that go along with it. One chip is the thing that generates the wonky clock. Another one is you could do it without it, but it's the one that's specifically designed to go along with the 8080 to expand out some of the signals from the chip because they're multiplexed. So you need to, it required 4 chips to do what the Z80 does in one. Number one, the interrupts that the Z80 has special features that can run faster if you use them correctly. It has a non-interruptible interrupt as well as a maskable one, or a non-maskable, I should have said, interrupt. In other words, one you cannot stop. So you're going to have like a power failure interrupt that no matter what it's doing, it'll wake up and go, I'm going to die, do something right now, kind of a thing. Okay, well, the 8080 did not have that. What else do we got? We got more instructions, and we'll talk about that in a minute as well. That's kind of the big deal here. The 8080 had 78. The Z80 has all the same instructions as the 8080, plus, again, as many more. Opcodes and so on. Why would they have so many instructions but they got more I'm not sure how to interpret that. Addressing modes are, if you don't know what assembly language is, these are how you get at your data. Do I get data out of a register that's inside the CPU? Can I get it out of memory? How else can I do this? Well, you got more modes, more options with the Z80. A superset, again, of what you got in the 8080. Working registers, how many, variables does the CPU itself know about if you don't know what a register is? Those are little memory bytes that are inside the CPU itself. And when you add two things together, you generally need to first copy a bunch of data into the CPU, into things called registers. Then you can add the registers together, and then you can take your results and store them back into memory when you're done. Now, that's a very simplistic description of the process. There are other ways to do it because they have other addressing modes, but most of the time what you do is what I just described there. And the addressing mode that you would use are, register direct addressing mode, where the operands of your comparisons and your additions and your subtractions and so on are values that are stored in these registers inside the CPU. The throughput, interesting that they put it in both columns. I'm a stickler for these details. It's my ADHD side coming out there. The Z80 is allegedly 5 times faster than the 8080A. Owning both, I'm not, well, they say up to 5 times, maybe. I never, no code I ever wrote, I don't feel that that's all instructions are not 5 times faster. I'll give you that. I think if you're careful and you use the block mode operations and things like that, you can go faster. Absolutely. Will it always go 5 times faster? No. 50% less space. The density of the instructions. Well, obviously, if you're going to just write a program in 8080A, take the binary and run it in the Z80, the amount of code it takes is exactly the same because it's binary compatible. It's also roughly the same speed if you only use the 8080 instructions. If you go through the entire manual side by side, you'll see sometimes the Z80 is 1 clock faster, 1 out of 5 or 1 out of 10 clock cycles faster for an instruction. And other times it's 1 or 2 clock size, 1 out of 10 clocks slower. And by that I mean these CPUs take, anywhere between like 3 or 4 clock ticks from this main clock over here to do one instruction, one call instruction or one of these LXI. In fact, this takes a long time to do. All these are pretty slow, relatively speaking. This one here is probably a pretty fast one. Increment the C register. That's going to be about as fast as any instruction is on this machine. And the reason I say this is because what you're doing is you're telling the CPU to add 1 to a byte that's already inside the processor chip physically in what we call register C. This one over here, what you're doing is you're telling the CPU to go out and fetch 2 bytes from memory and then store them in this 2-byte register that can hold 16-bit values. Well, the C only holds an 8-bit value. This is going to have to go fetch a byte, and then store them into this register here, which is going to take a lot longer than it is to just simply add 1 to something that you already got. All right, because it doesn't have to go get these other things. All right. So you're going to see a ranging difference in the instruction time of execution is what I'm getting at. So a 10 cycle instruction on an 8080 could take 9 or 11 or something like that on a Z80, depending on which one it is, okay? They're roughly the same speed in terms of the number of clocks that are consumed to do something, okay? However, the Z80 can have a faster clock speed. The clock can run faster, the 500 nano on the 8080 versus the 400 nano period on the Z80. So it's just faster because the clock can go faster. But on average, I'd say it's about the same number of ticks per instruction. Okay, so what do you got here? This top manual's a big manual, 200 plus pages, but it covers all those extra chips that we just looked at in that advertisement for the 8080, the support chips, okay? This one down here focuses only on the assembly language, so let's open that one up, and that's really what we're here for today. I'm gonna get that on the screen. There we go. Okay, so if you open this up, what do we got here? What do we got? Let's get it all on the screen here. 91 pages, all right? Now, this is everything the 8080 can do in terms of its programming. 91 pages. You can read this in its entirety and understand every single thing it does. Same is true about the 6502. I'm not going to diss that. I'm not a 6502 guy. Yes, I have a VIC-20 around here somewhere, and all the Apple guys and the Commodore guys, all 6502 stuff. A lot of 6502 things going on. That's a whole different style of processor design than the 8080 and the Z80. And it actually can go faster. given at the same clock speed, it uses less cycles per a lot of its instructions. Run in far less number of clocks. So 2 megahertz 6502 is about as fast as a 4 megahertz Z80. That might even be still faster. So it really depends on what you do with those clocks. All right, I digress. But my point is that the 8080 and the 6502 are comparably complicated in terms of its instructions. And by that I mean you can fit every instruction that this machine does on one single page and be readable without a font that's super tiny. Somewhere in here, there's an instruction set summary in it. And I suspect that it's actually stored in this other manual here, so I guess there's a reason to have them both. Somewhere I actually have a hard copy of these manuals. I don't know where it is right now. Somewhere in here, I'm pretty sure. Come on, don't make me a liar. ROMs. So basically, it's going to give you a 15-page summary of the instruction set that you get in 91 pages in the other manual, is my point. And I think that this table here on page 4-15 is the one I'm thinking of in my mind. It's 2, 3, 4. Come on, 15 right here. There you go. There's every instruction that the 8080 can do. You can't do this on the Z80 because it has at least twice as many from the get-go. But you can get this all on one single sheet of paper printed out, which is what I did when I was a kid, when I was using the 8080 assembly language for things that I was working on. And then you can just mark it up or make another Xerox tomorrow. Make your own little green card, as it were. Very simple. This is achievable. It's an attainable goal. You can actually do this, even as a child. But as you move on, like at the Z80, you get twice as many, just more and more and more and more. Nowadays, you get like millions of pages in one manual for one chip. I don't know how many pages the big Intel processors have now, and the AMD ones. It's at least 2,000 pages long. A lot to understand. I gotta wonder if anybody actually gets it all. I don't know. In any event, okay, so what I wanted to do is make sure that we all understood why I just added these things. If you get alerts, if you're following the repo and you're around, great. If you're just starting out, you may want to glance at this or at least understand that it is here. Because if you want to understand what's going on in the CPM manuals, all the instructions are documented in this nice little short manual here, and they give you a really nice description here. What does the stack pointer do? What does the program counter do? What is memory and all this other stuff? If you're really, really starting at the beginning, and somehow you got it in your head that my videos are the ones you want to watch to learn this thing, and you're starting at the beginning, you may want to look at this manual, okay? Because I just skimmed over it the other day, and I said, you know, I did everybody a big disservice by not mentioning this before. And I'm gonna, like I said, I'm gonna go find a place to put this earlier on in my playlist of videos for the Z80 Retro, so that you can know what to do, because I've had some questions over the course of time, and I always kind of felt a little bit bad diving into the Z80 without addressing this particular issue, okay? So here it tells you here, before I execute a pop instruction, what does it do? Here's some memory, here's a value in the stack pointer register, which you saw they described up here. You know, what is the program counter? What is the stack pointer? What's it for? That kind of a thing, okay? How does memory work? Here's the numbers, and so on, okay? So this may give you a toehold that I may have left, you know, might not have given you a, what do you want to think? I run with that analogy, a sturdy enough piece of ground, a turf to stand on, okay? This may be worth an eyeball, okay? They even talk about subroutines and the condition bits, and we'll see those in a minute when it comes to what's different about the Z80, okay? This is it right here. These so-called condition bits are what we call the flags on the Z80 and a lot of other processors, okay? What else we got going on? How is assembly language used? What are they about? You know, how do these bytes mean something? Where do they come from? What is the syntax? And there is the whole thing in a nutshell. Here's a label. Here's an instruction. Here are the operands. And here's what the instructions all mean down here as you go. This is all the whole world right in a nutshell. Back in these days, everything was super duper simple because the assembler itself had to run in 20K of RAM. If you go back and build and install CPM 1.4, which is what I started with, you can do it with 20K of RAM. And you can run the assembler, and you can run the debugger. It's like, can you imagine, in today's operator, oh, I only got 100 gigs of RAM and it won't fit, blah, blah, blah. Oh, my Lord. 20K, people. My point is, you can't do much in 20K. Therefore, it is really, really simple because it is really, really limited. All right? So, again, this is attainable, even to a kid. But you gotta want it. Like I said, I had a lot of frustration learning this. And what is two's complement? Why do we have two's complement? Blah, blah, all these great questions. Even if you're studying computer science in college, this sort of thing does come up. And you're better off knowing it than not when you're debugging a program you don't understand something, okay? All right, so that's why I added this manual, because this is the manual that was read and referenced and used when all the code for CPM was written by the guy that wrote it and wrote all these manuals for it, okay? There's your, with the 8080 assembler and the DDT debugger and so on, okay? So that's really the whole ball game. Now, let's take a few minutes here and talk about the differences between the Z80 and the 8080 beyond that simple sheet that we saw on the Wikipedia page. And to that end, you can just throw out, do some Googling around and say, what's the difference between the Z80 and the 8080? What's really different about their instruction sets? Which I did. I Googled it. I saw this. And I'm like, this isn't too bad a description. Somebody nicely summarized the whole thing. So the initial answers here are okay. But this down here, this is a really good answer. I skimmed over it and I'm like, oh, I didn't even know this one, and so on. Now, of course, this may not be all 100% correct, but the main thing is this, okay? The Z80 has more registers and it has more status flags and things like that. And they've purposely changed some of the meaning of of at least one, if not a handful, as you'll see, of these instructions. And what they do is when they're done, there's like a status that said, if, for example, one of the flags is using, if I add 1 to a register, did I get a value that's negative? Did I get a value that turned into 0? Like, when your odometer overflows, like the Y2K problem that we're all overwhelmingly familiar with. If you add 1 to some value and get 0, then you know it used to be a negative value, or it was a large positive value that just overflowed and went back to 0, okay? So there are flags, there are status bits for that. And the Z80, after certain instructions, like one of them is the half carry flag. And you can read all about what that means in the documentation we just looked at. This flag works differently on the Z80 than it does on the 8080. And one of the reasons I did this is so that you can write a piece of code that will get a different answer on the 8080 versus the Z80. That way you can write a program that says, am I on a Z80 or not? And if I am on a Z80, I can then proceed to use advanced superset, the Z80 extended instructions. Otherwise, I cannot. You might generate an error and say, you can't run me because I'm only work on a Z80. Or you might actually have a program that has 2 different sets of subroutines. And you could call the 8080 version or the Z80 version. And the reason you would do that is because you can write code that runs faster on a Z80 because it has more features and things specifically for that purpose if you need those features. Otherwise, you can do it the old way. And this was, this was very important back in the day, right? Even on a Pentium machine these days, not a Pentium, the Intel architecture or whatever, I still call it a Pentium. Because, it's not a 486, it's the next one. they have ways to ask, do I have, you know, the MMX instructions, are they on here? Or do I have this, that, and the other thing? And you can get an answer back from the CPU. They've, by now, they have like explicitly have status bits and configuration registers inside the CPU where you can just explicitly say, do you have this or not? Because they have so many options that the Z80 has one. You're either a Z80 or you're an 8080, okay? So they can have more of a pick and choose smorgasbord in the giganto processors of today. So that's why we have some of these instructions work a little bit differently. The other differences have to do with speed, and here's what they're saying. This can take 11 cycles on a Z80 or 10 on an 8080, and then other times it's like 10 on the Z80 or 11 on the 80. Like I said, they're about the same if you're going to execute the 8080 subset instructions of all the Z80 instructions. Some things on the 8080, this instruction only works, whatever that means, right? It'll do something, but it only gives you useful results for the purpose of this instruction as documented for the 8080 after an addition. And on the Z80, it works a little bit differently, so that after a subtraction, you can also use the instruction to get meaningful, useful results in the theme for the instruction the way it was designed, okay? And I was careful how I said that, maybe not careful enough. Call me out in the comments below, because a lot of times instructions get used for purposes that they were not originally designed for. They're weird behavior that, oh, well, they'll never use it for, you know, anything other than what it was intended for kind of attitude. No, there's always somebody out there that goes, oh, I can use this wonky feature that was, you know, this coincidental side effect of this instruction for other purposes when you have use it in a different context, okay? I mean, whatever it's going to do is going to be reproducible. No cases am I aware of that do the 8080 and the Z80 instructions generate a random result. They all do something. Whether it's useful or not is another question, and it depends on the context within which you use it, okay? So there you go. There's the 8080 instruction mnemonics, the manuals, where to find them. The Z80 ones, I've shown enough in this channel that we don't have to worry about that. What I guess I could do is a concluding thought. That's the technical manual about the CPU itself. Assembly Language Programming Manual. Without the OCR errors present in this manual. Yeah, I mentioned that in one of my videos about be careful when you're looking at the modern editions of old manuals, because when they scan them in, I'm going to risk it. Sometimes they run them through OCR and the OCR doesn't work, and then I don't know who they hire for these things. You'd think for the amount of people that work at these companies, somebody could go through and at least eyeball these things after they're checked. So this is like the original Z80 manual. This is one I used to learn how to program assembly language for the very first time I ever wrote an assembly language programming. It was the this documentation. I won't say this manual, because I got a copy of this because this is included in the appendix of the EdTES manual from Microsoft to run on the TRS-80. So this is what I used. And this is what I'm talking about. When you OCR like this, sometimes it puts the letter C in here instead of R prime, okay? Which, in fact, it does it right here if you go get the modern one, and I laugh about that in another video. I won't have to waste our time for this. My point is, you might want to go get the old one again if you're not used to and aware of what. If you're not only using this as a refresher and a reference, you might want to get this old one, not the new one. The new one has errors. They introduced errors over the course of time. Okay, so what do we got here? This is a great example. Load R, comma, R prime, which I think is a terrible way to express this, because they actually do have an R prime register. which this could be confusing on the Z80. So if we look at the same instruction on the 8080, okay, let's see, we go. Put this up here. This would be a move instruction. Move immediate. Let's look at move immediate, and then let's look at move. Where's Mr. Move? Add with carry. Where's the regular old move? Store A. Come on. Oh, these are immediate. Immediate means that you have an operand in there. Oh, fine, we'll do move immediate, okay? Move immediate data, page 26. It'll be in the same range of instructions, I'm sure. Here, where are we? Are we on 26 yet? Are we there yet? 21. And there is 28, 27, 26. Move immediate data. Okay, here we go. Here we go. You have some bit values here, and you have some data there. So this is a 2-byte long instruction. And the opcode is MVI. The operand would be the register to move it into and the value. So what you have here, and this shows you how it gets put into the binary data, you have to have an 00, and these have to be a 110, and these bits in these locations in that order, and then a 3-bit value that represents which register you're going to put it in. Okay, and somewhere in the manual it'll tell you the 3-bit values for the register A is this and B is that and so on. All right, so as long as you have a 1-byte value that looks like this, and I happen to know a 3E is the move immediate for the into the A register, and then the data would go over here. An 8-bit data byte value would go over there, okay? So that's the MVI register, comma, data, like that, all right? Now, in Z80, you would say load register, comma, data. And this is, of course, the register to register. Where's the register? RN is what they say. Okay, here we go. A numeric value goes into the register. I changed my example midstream, and you can see I got a 00 followed by a 3-bit register number and a 110. Poorly documented because this arrow points too far, in my opinion, because it's supposed to represent this 3-bit value in here. But I think you can figure that out. And here's all the 3-bit values that they give you. And again, this manual, the Z80 manual here, in my opinion, this was like a gift from God. If you're starting this for the first time, look what they give you here versus the 8081. Now, the 8081 is perfectly fine. It does give you, here's the assembled data, and here's some examples of the regs and all that, but the register bit values are stored elsewhere, and you got to refer around. Again, fewer instructions, real easy to understand. But look at this on one page. It tells you everything from the 8080, plus it reminds you, this is copied over and over in this manual because of this. Every time there's a 3-bit value inside of instruction that represents a register, they give you this table again. It tells you how many clock cycles it takes to do it. If you do this, does it affect any of the condition bits, the flags? None will change. And then that gives you an example, and it says if you do this, then the constant register E will equal A5, which says load, in my mind, I always think of it, load into this thing on the left, comma, the value from the guy on the right, okay? Blah, blah, blah. It will be A5. That's how you get an A5 into the E register, okay? So over here, it's nice and simple, but it doesn't tell you what this means. All right? This is great. It's concise. It's right there. Super summary. Instruction M1 loads H register with a byte of data and there. The instructions at M1, there you go. Oh, it does give you the run. Handle with this, which is 3C. Likewise, the M2 loads the L. Okay, all right, I stand corrected. What they don't show you in here is that table of the 3-bit values of all the registers over and over and over again. The table is in this manual for the 8080, but it's on a special page that says here's the values, okay? So both of these do give you a very nice description. They also launch into what happens when you use M. This register called M on the 8080 is a really interesting feature which this grammatically is very different than the Z80, which is why we're here today. If I say move immediate M, comma, this, what that instruction is in the Z80 is load, open parenthesis, HL, close parenthesis, comma, 0FF. Okay? And what that means is in 8080, when I was writing 8080 code, I would think move into memory M, the value FF. Well, where in memory does it go? Well, it goes into memory at the address in memory that's stored in the HL register pair, and you'll see that written down here somewhere. M3 down here causes the data at M3 plus 1. The second byte in this instruction here, 36 is the opcode that includes this M value, and the FF is the value you want to store into the destination, okay, which is the memory. But where? It says causes that to be stored in memory at location 3CF4. The memory is obtained by concatenating the contents of the H and L registers into a 16-bit address. So the instructions at M1 and M2 could be replaced by the single instruction load X extended. And in the Z80, you would say LD HL, comma, 3CF4 and hex. Okay, so these, what you recognize the similarity, the kind of, what's going on, the style of the 8080 instructions versus the Z80. You can easily read one and think of the other and jump back and forth, okay? That's the whole point of this whole video, is to make sure that you're able to do that when you're looking at older doc that's all 8080 style. Okay, notice that they loaded H with 3C, L with F4, and then they said move into memory at the address in the HL register pair, which is 3CF4 because of this. That's what they say there, right here, okay? And put the value FF into memory at that location, okay? Well, the Z80 manual, what do they say about that? We may have to go back up. It'll be documented in the 16-bit. That gets a value from memory and put it into register. We need the other way around. So in 8080, this instruction here would say load register, comma, M. And whenever you see HL in parentheses like this, it's saying that this is an indirection, okay? Is what we call that. Go into memory at the address that's in HL, get the value and put it in R. So I don't know where the other one is in this manual. This is the index register one. This does not exist in the 8080. This is one. These are some of the add-on fancy instructions. So here is the equivalent one documented for the Z80 load into memory at the address in HL, comma, R. I think this is easier to read, easier to understand. LD always makes more sense to me anyway than move. Move always suggests to me that you're vacating something along the way. I'm moving it from point A to point B, and thus from point A it's no longer there in my mind. I found these to be confusing, but they should have called it copy. And what you're really doing is copying it from the source place to the destination place. All right. So this is a little more explicit about what's really happening because HL holds the address to where you're putting the data, and the parentheses say there's an indirection, which means don't put it in HL, put it in memory at the address in the HL register pair. Again, you see the if you want the A register and so on, which of these 3 bits do you use, and how long does it take to do? Here's an example. If I say what B over there, load into memory at HL comma B, and you say if B has whatever 29 in hex and HL has 2146, then the memory at 2146 will then contain 29 after this instruction completes. So each page, they get the whole thing slammed out in your face. Plenty of room for penciled in notes around here, which my manual had much writing in the margins. And back in those days, absolutely. So again, so these are the differences. Here's the manuals that you want to use to figure out what they mean. If you can't figure out what DAX does or, XTHL or whatever, and so on. You can look up all these things. Load accumulator direct. Here, I thought that was MVA. Oh, LDA, low high. Oh my gosh. Yes, this is okay. I forgot that this was what they called it on the 8080. So even I got to look these up every now and then. LDA, comma 300 in hex means go into memory at address 300, take the value out of there and put it in the accumulator. And in the Z80, that would be a load A, comma, open parenthesis, 300 in hex, close parenthesis, because they're way more consistent. And the pseudo orthogonality is better on the C80 than it is on the 8080. If we go find that one, who knows how long it'll take me to figure that one out. Well, it'll look like this, RN, but N will be in parentheses because it's an indirect, and you go into memory and get it. And load A from memory whose address is in the BC register pair. DE, here you go. And N, they put two N's to let you know it's a 16-bit value that represents 2 bytes with the 2 N's, okay? And they said it's encoded with a 3A followed by the 16-bit address. And it'll actually be backwards. If you wanted it to read out of, hexadecimal 1, 2, 3, 4, you'd see the 3, 4 here and then the 1, 2 down there. I'm pretty darn sure of it. They don't make that overwhelmingly clear in here, but that's how the machine works. And it'll say if you're going to go that in memory and that's stored there, you do this and it ends up in the accumulator. This one here, we'll see where it says low address, high address. Like I said, if you want to read it from 1, 2, 3, 4, you'd see the 1, 2 over here and the 3, 4 over there. So it would be backwards because that's what we call a little endian value. And that's what you would, that's how you store it in there, okay? So again, here's the op code. What do we got here? That's a 3 in hex, 0, a 3. What was it? 8, 9A. So this would be a 3A followed by the addresses. And this one over here says a 3A followed by the 2-byte addresses. All right. So, like I said, I wanted to make sure that everybody knew this existed, where to find it, what it means, and how you can make sense when everything I talk about looks like this, but the manuals that you read for CPM look completely different. Okay. That's because they're written in 8080. The Z80 can run all the 8080 instructions as they are, with some subtle differences that have no impact on any practical program, and in a way that you can use to figure out programmatically whether you're on a Z80 or an 8080 style CPU and react accordingly. Okay? And you can now make sense of the alteration guide and all the source code that they give you in here. Now, because nobody on earth would ever want to use a chip that requires 3 separate filtered and regulated voltage supplies and a non-overlapping clock and all this funky stuff and extra chips and extra expense. As soon as the Z80 came out, we ended up with ZSID, and I think I mentioned this briefly once in one of my videos. If you look at this, this is a Z80-based Symbolic debugger that kind of goes along with one of their assemblers, and you'll notice that was 1978. So after the release of the Z80, right? So how do you run SID? And then down here it'll talk about ZSID somewhere. Oh, I see. There's one manual for both. They all both work the same way. Command input, how to type things, how to enter in numbers. This is like DDT, but the idea is it's symbolic. So if you have a program with source code that you assembled, and it is a symbol table, and this is all advanced stuff. So where they're talking about symbols and symbolic stuff and so on. What it'll do is it'll go back into your source code and figure out, oh, this is a value in memory that has a label on it in your program, and you called it XYZ. But it's really stored in address, 12345, and its value is, 2F or whatever. Okay, so this is a symbolic debugger, while DDT only does 8080 instructions, and it does not do symbolic debugging. It does just the raw binary, and you kind of have to keep your source code on hand and refer back and forth as you go, which is usually not a bad idea anyway. And in here it explains how to do that. If you read the DDT manual, it says here's how you run it. And then it says, take your source code and mark it all up like this as you go. And it tells you if this is your source code, here's where everything is and how it all will be. In, when you assemble it, it'll mean this. And it'll say when the assembler runs, it'll tell you here's all the hexadecimal values that represent all the instructions that you just saw in the documentation. Even if I wrote this in Z80 and I did not use any instructions that are not on the 8080, it would disassemble it as if it was on an 8080. When you run DDT, it would. And you would see the 8080 mnemonics in here with the exact same binary and hex values over here would have the same thing when you run DDT. So, so it tells you here's what you're going to do, here's what everything means, and blah, 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 blah. And if you use a Z80 debugger, it'll have twice as many registers as this. It has A and A prime, B and B prime, D. Well, these is B, C, D, E, H, L, stack pointer, the program counter. There's not two of those, and there's not two stack pointers either. But there are going to be two flags, two accumulators, and so on. And you can, swap the registers back and forth. It's kind of a cool thing. It's quite often used in interrupt handlers and stuff. I don't get too much into that in here. I didn't really talk a lot about code design other than here's a program that I wrote when I was writing my BIOS for the operating system to just get the thing going. I made a lot of assumptions in the series, and this is one of them that you know which instructions stacks B is when it's on the Z80. What does that do? What is it supposed to look like? All right, and now you know how to look up all that awesome stuff. INR, INX, what's the difference? This is an increment register B. INX is an extended increment of register BC, okay? So, the Z80 makes it a little bit more obvious what you're doing in these cases, because in the Z80 you would say INC for increment, and you would say BC, or you would say B. Depending on what you wanted incremented. Okay? So anyway, it goes over a lot of the stuff in here. And if you want to start the way we did in 1978, this is what you had to work with. Now, bonus time. Usually I go about an hour. I got 5 minutes according to the clock on the wall. What do we got here? Google around for 8080 emulator, simulator, whatever. Okay? And that's what I did here. I found this site. Now, there's a bunch, okay? I'm not going to say one's better than the other. This is the first one that I found that looks like this, okay? Now, if you really want the true experience, you got to do it this way, okay? Now, when I first started, I was on a TRS-80, so I had a keyboard and a screen, which we're all used to and familiar with today. But, if you really got into this back in the day, you'd have one of these or the Altair, which the same simulator I just showed you would be also supports the Altair 8080. That might work. 8800. There you go. The IMSI 8080 and the Altair 8800, even though it had an 8080 in it. The reason I want you to see this is I want you to see the front panel, because it's marked differently than the 8080, the IMSI one. See how these are grouped into 3, 3, and 3, and so on? What are they smoking, right? The reason they're grouped this way is because the vast majority of the instructions, this is an 8080 CPU in it, in almost all cases, when you look at the doc, I should close all these extra windows here. You see how there's 3 here? There's all these 3 and 3 and 3. They're grouped into 3s. Not always. There's an example that was not. You see this one here? There's 3 bits, and there's 3 bits here. There are 3 bits here, 3 bits there, 3 bits there, 3 bits there, blah, blah, blah. When you say move A, comma, C, I wish I could find that instruction in this stinking manual. One of the problems with this is I moved my mouse around because they didn't know CR, this particular version, so you can't do text search on it. So we'll be looking around for 20 minutes. But my point is, when you would encode these instructions on a machine, these older machines, 1975, 1976, prior to 1980, you know, when more people could afford a terminal, the things were over $1,000. They cost more than the darn computer. If you really got into it, you wanted to start from scratch, you used a machine that had switches like that on it. And if you had an 8080, you got very used to seeing things in terms of the 3, 3, and 2, because almost all the instructions were this way. And every time that you would have a register in here, or an operation in a group of instructions, the operation would have a 3-bit code. The register you want to use would have a 3-bit code, and so on. And they're always grouped in these groupings of 3 and 3. Here's a great one. Move immediate, right? We looked at this before. You put the register in there, and everybody would know that an A was it was a 7, I think, and B is a 0. What was it? The Z80 makes it more obvious. The encoding is not what I would have expected it to be. I would have thought that A would be 0 or something like that, but that's not how it is. A is like the biggest value, and M or something like that is 0. I don't remember. There you go. A is 7, and B is 0, C is 1, and so on. And it turns out that the opcode for this is the exact same as the opcode in the 8080. You would put M in there as a fake register, okay? So look what's going on here. There'll be 7 of these. 1, 2, 3, 4, 5, 6, 7. What's missing? 110 is missing. That, if we look up the load, load R, comma, open paren, and end close, you would see in the 8080 is just another move, okay? This is the SID manual. I don't know what I'm doing here. The SID manual. It would just be another move in that register. In here, you would just put the register for M, which represents the HL in parentheses. So they didn't single out this idea that HL could be used as a address memory pointer type of thing. It was just another one of these, where the source code for the Z80 made them look as if they are unique and different, as if this is somehow a different instruction altogether. Look at the encoding, 01110, for put into a register the value from memory, and over here you would say, come on, all the pages I got to open here. You'd say put it into a register from the memory over here, right? The 110 is what we're looking at, the 00 and the 110, and you just put the register value in there, okay? In fact, they even do that right here, and they say that the opcode for this thing is a 36. So that's a 3, that's a 11, and a 6 is an 0110 in hex. But in octal, it's 0, whatever that thing is. 110 would be a 6, 6. So, you know, if you went back in the day, and a lot of guys did octal, and because of this, okay? So the screen on here, or the screen, the switching grouping on there is actually not a bad idea. Okay, to have them grouped in octal like this. But I never learned octal back in the day. I hit the ground running in hex, and that was just the way it was for me. You can see these little arrows in here and these other groupings so that you can see them in more close to the hex. What do you got? Sense switch. You've got, I don't know, the way these lines are in here to represent the addresses and stuff is my point. So this was really laid out to look at a little bit more like octal, because that's how things were encoded. All right, that's why that's that way. I thought in hex because I went with the Z80 from day one, and all the dock was in hex. And if you ever saw an 8080, people would group the colors like this. So you would think about 4-bit values instead of 3-bit values, and therefore you would end up in hex. But look it up here, hex and octal. See these little slugs? They still showed you these groupings, so that you could easily in your mind say, oh, if I want to do a move immediate and I need a 066 for the accumulator, you could easily say 110 right here and know where to put that. Okay, so that's why these markings are the way. I guarantee it. I was never told this, but I guarantee you that's why these marks are like this. That's why the switches are the way they are on the Altair, and so on. Now, I show you this because this is actually pretty popular. If you look at the Z80 pack link right here, and this high nibble guy, all right, you can actually buy this. Okay, it's about a 2-inch deep version, just the front piece of this thing that looks exactly like an MSI 8080, but it weighs 90 pounds less. It uses far less power. It does not have a real 8080 in it. It's got like a Arduino or something like that in there, or an ESP32 actually, I think is what it has. And it just runs an 8080 simulation program, and it lights up the LEDs as if you're doing the real deal. And if you look at how to use it, this is very popular. You can either buy the physical thing, or you can open this up. This is running on a Mac, obviously. It has a graphic display, and you can click your mouse on these switches and do it this way for free, okay? Or you can buy this box and do it all mechanical and everything else. And because this is super shallow, you can stick it on a shelf, hang it on a wall or whatever, and it's pretty cool. I think it even has Wi-Fi and stuff like that, because it has what the ESP32 has. You can connect it up to your PC, and you can have all these windows, and you can have a display, and you can control it this way and run it with a debugger and all that other fun stuff. But honestly, if you're going to do this, I wouldn't buy this thing. I would just run the simulator here, which comes from Z80 Pack, which will run on your Linux and your Windows and so on, which is what this runs inside of itself anyway, or something very similar to it, okay? And on your display, you can still do all this fun stuff. You can boot up CPM. You can run all the 8080 code. That's exactly what they're running right here. Con equals CRT, and these various commands that you can use and run all these CPM programs in here. What has he got? Xsub, boot, all the usual stuff, plus a few other things that are very CPM-ish things on your drive A. BIOS.asm, that's the BIOS source code that matches this thing that we were just looking at right here, which is your example. Oh, that's your putsys program. In here, there's a sample BIOS. It says here's, you can start with this if you need to write your own and then fill in what's missing. And I go through this in my other videos when I wrote mine in Z80. There's the cold start loader. There you go. That's a real one. This is the whole BIOS for a system, the MDS system. And the latest version he wrote was 1979 as per this manual and so on. All right. So I think I went through some of this when I was doing mine, and I kind of, and here's me trying to fix this gap. And I said, well, these are all 8080 instructions. Look them up. We're going to do it in Z80. And now you have the dock to do all that fun stuff. And if you're watching this before, spoiler alert, this is what I'm referring to in the later videos when I say things like that. Okay? Now, if you really want the real machine, or at least to simulate the real machine, go find this Z80 pack, or find the this physical machine. What does it go to? $300. You can buy this, at least at the time that this was written, at the high nibble. What has he got over here? Does he still sell these? Is this still available? Blah, blah, blah. It's full scale. 17 inches wide to fit in a 19-inch rack, because they had these brackets about 1 inch either way if you actually get a rack-mounted thing. And it comes with all kinds of fun stuff. Max 232 style thing. Wow, you actually get a DB9, a real serial port on there. What do we got? These have a dual core Wi-Fi and all this fun stuff. If you buy the physical thing. use the USB thingy. It's got all this fun stuff. It runs the 2.2 BIOS. And in my series on the Retro, this is all the same stuff that I did. I wrote a BIOS from scratch in Z80 Assembler. And he's also talking about IMSI, SIM, and Z80 Pack. Okay, so then we're making full circle here. And he's got the same little images we just saw, blah, 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 some notes. All right, so if you really want to get into this, you've got to get the old doc. If you got disoriented because I was an idiot and didn't talk about the 8080 opcodes, the doc doesn't match what I'm doing, now you've got what you need, all right? So let me know what you think. If I missed something, if I need to do something else, let me know in the comments below. Thanks for watching. I'll see you next time.